In part 2 of Vectors in Two Dimensions, we're going to work on modeling velocity and force vectors. Well, think about an airplane. When an airplane travels, let's say from Los Angeles to Chicago, it's following something called the jet stream. The jet stream is the wind that's pushing from west to east. What ends up happening is that the airplane travels faster than its actual speed. We call this the true velocity. However, if the airplane instead was going from Chicago to LA and it's going against the jet stream, it would be going slower than the actual speed of the plane. And again, this would be this true velocity. Let's say we have an object which is going in this direction. We'll call it north. But we have a wind that's pushing things in this direction. So if I have this vector here, the true velocity would be the diagonal of this figure here. So what we're going to do is we're going to have two velocities. We'll call this one u. We'll call this one v. And we'll call the true velocity w, which is the sum of the other two. In order to find this thing called a true velocity, we're going to have to talk about the horizontal and vertical components of a vector. Well, if you have a vector, and you think about a vector on a coordinate plane, there's going to be this horizontal component. And the horizontal component of this vector is going to be the magnitude of the vector times the cosine of theta. Theta is the angle from the horizontal up to the vector. And then there's going to be this vertical component. The vertical component is going to be the magnitude of the vector times the sine of that angle. So a vector could be written in component form. Oops, I should not use the bars. As the the magnitude of v cosine theta I plus the magnitude of the vector sine theta j. And that's how we can write it in component form. Let's do an example of true speed using these component vectors. An airplane heads due north at 300 miles per hour. It experiences a 40 mile per hour crosswind flowing in the direction of north 30 degrees east. Express the velocity v of the airplane relative to the air and the velocity u of the wind in component form. Well, the airplane's easy. It's heading due north. So the airplane, since it's heading due north, is heading in the j direction, which means the I direction is 0. So it's going to be 0I plus 300j. It's the wind that we're going to have to do a little bit of work on. The wind is traveling at north 30 degrees east. That means this is 30 degrees. That's how the navigational headings work. Except that when we use theta in our component form, we don't want the angle from the vertical. We want the angle from the horizontal. So instead of using 30 degrees, we're going to use 60. So u is going to be 40, because it's traveling at 40 miles per hour, cosine 60 degrees I, plus 40 sine 60 degrees j. And then we can simplify that. You can simplify it to be in radical form, so you can tell me that this is going to be 20I plus 20 square root of 3j. Or I will also accept this in decimal form for this particular unit. It would be 34.64j. The next thing that we want to do is we want to find the true velocity of the airplane. The true velocity of the airplane, we'll call it W, is going to be the sum of the airplane and the wind. So when I add them, I'm going to add the I components. So it's 0 plus 20, which is 20I, plus 300 plus 34.64, which is 334.64J. After we find the true velocity, we want to find the true speed of the airplane. Remember, speed is the scalar quantity. Scalar means not a vector. To find the scalar quantity, you have to find this. Remember, this does not stand for absolute value. This stands for magnitude. And you find the magnitude by taking the square root of each, the square of each component and adding them. And then taking the square root of that quantity. When you do that, you will get approximately 335.2 miles per hour. So the wind is actually making the plane go faster. What if I wanted to know its actual heading? Because in order for the plane to actually go north, it would have to travel at an angle. Well, we have a way of determining that angle. We do the inverse cosine of b over a. That means I'm going to take the inverse cosine of 334.64 over 20. And that's going to tell me the answer is approximately 16.7 degrees. That's 16.7 degrees this way. But we need to know this if we want to give the navigational heading. All you have to do is subtract 16.7 from 90, and you get 86.6. So really it's heading north 86.6 degrees east. A woman launches a boat from one shore of a straight river and wants to land at the point directly on the opposite shore. If the speed relative to the water is 10 miles an hour and the river is flowing east at a rate of 5 miles an hour, in what direction should she head the boat in order to arrive at the desired landing point? Well, I've drawn a picture here to kind of let us know what's going on. The woman in the boat wants to head straight across the river, so straight in what we're going to call the northerly direction. The problem is that the water is flowing east at 5 miles an hour, which means it's actually pushing the boat towards the east. So in order for her to go directly north across the river, she has to go in an angle kind of to the west. We want to find that angle. So what we're going to do is we're going to start by finding the velocity of the water. I'll call that u. Well, the velocity of the water, since it's heading straight east, and that's the I component direction, is going to be 5I. The boat, we want it to go straight, but it's really not going straight across. It's really going at an angle so that it appears that it's going straight across. So the boat is actually going 10 cosine theta I plus 10 sine theta I. Its true velocity, W, is the sum of those two. It's 5 plus 10 cosine theta I plus 10 sine theta I. 10 sine theta j. I know it's a video, but you got to tell me when I'm making things incorrect. All right, let's try that again. That should be j. All right, now here's the deal. So when she goes at this angle, what's really happening is that it appears as if she's going straight. So it appears as if she's going in the j direction. Well, if she's going in the j direction, then what appears to be happening is that the I direction would be equal to 0. So we're going to set that component equal to 0 and solve for theta. Well, you subtract 5, you divide by 10, so you get cosine theta is equal to -1/2. And when you put this in the calculator, remember you need to be in degree mode in this particular chapter. We're going to find out that it's 120 degrees. So she needs to head the boat 120 degrees from the horizontal in order to get the boat to actually head straight north. If we want to know what that is as a component, or as a navigational heading, the navigational heading would just be this. It's always the angle from the vertical. Well, if it's 120 degrees, then this part is just 30 degrees. So we would say that it would be north 30 degrees west. Force is also represented as a vector. Intuitively, we can think of a force as describing a push or a pull on an object. For example, a horizontal push of a book across a table or a downward pull of the Earth's gravity on a ball. Force is measured in pounds, or in the metric system in physics class we would use newtons. So if a man weighs 200 pounds, he exerts a force of 200 pounds downward on the ground. If several forces are acting on an object, the resultant force experienced by the object is the sum of the vectors of these forces. So in this next example, two forces, F1 and F2, with magnitudes 10 and 20 pounds respectively, act on an object at point P. Find the resultant force on P. What I need to do is I need to write the component form for each of these forces. The resultant force will be the sum of them. So, again, at the beginning it said the magnitudes of the forces were 10 and 20 pounds respectively. So for force 1, it's going to be 10 cosine 45 degrees I plus 10 sine 45 degrees J. And if I go and I simplify these, I'm going to get 5 the square root of 2I plus 5 the square root of 2J. Force 2 is going to be 20, that's its magnitude, cosine of 150 degrees I, plus 20 sine of 150 degrees J. 150 degrees has a reference angle of 30 degrees, and it's in quadrant 2. So the cosine of 30 degrees is square root of 3 over 2. So this is going to be negative 10 the square root of 3I. And the sine of 30 degrees is 1/2, so this is going to be 10J. The resultant force will be the sum of these two forces. So the sum of these two forces is going to be 5 the square root of 2 plus negative 10 the square root of 3J, I, plus 5 the square root of 2 plus 10J. If you put these in decimal form, you're going to get approximately, about negative 10I plus 17J, and that's approximately. And that is force vectors and other directional vectors on objects.